We just spoke about empirical entropy and zero order empirical entropy and then high level empirical entropy or order K empirical entropy. And we said that the high order empirical entropy is really just grouping characters by their context and then applying zero order compression for each context. Now, I said at the end that, of course, there's this trade where the more context we consider, the greater we make this variable k, the more codes we have, and the more unwieldy our method becomes. And I said, however, that there's a trade where zero order entropy, while applying a zero order coder, like a Huffman code, for example, is very, very simple and efficient, that it doesn't get as much structure out of the string, and it therefore doesn't benefit from as much predictability when it goes to produce its encoding. But maybe there's something we can do to the string first so that zero order encoding is actually something that's just as beneficial as high order coding. And so that's what we're going to talk about here. And this is the first encounter with the Burrows-Wheeler transform. We're going to talk about the Burrows-Wheeler transform for many subsequent lectures, but this is really the first one where we start to tackle it, and in particular we want to see how it can have an impact on this compression question. Okay, but before we see the Burrows-Wheeler transform, we've got to talk about rotation and notation. So let's talk about rotations first. What is a rotation of a string? So here I've got this string, bonbon. What do I mean by a rotation? I just mean that you start with this string bonbon, and then you have a way of taking this string and snatching a character off of one end of the string. Let's say we take it from the beginning and put it on the end instead, right? Should sort of make intuitive sense, a rotation. It's sort of like we're taking, sort of like as though this string were written on a circular piece of paper, right? And it's sort of like we're just taking the circle and going chunk, and we see a new string where the character has gone around to the other side. Okay, so that's the first rotation, but we can keep rotating. So we can, for this word here, we can take the O off the beginning and put it on the end. We can take the N off the beginning and put it on the end, take the B off the beginning and put it on the end, etc. And you can think of these 1, 2, 3, 4, 5, 6 ways of doing that. Before we actually get back to the original string, you can think of those as all the rotations of the string. Okay? It's another way you could say it, instead of thinking of it as repeatedly taking a single character, moving on to the end, you could think of it as all ways of partitioning the string so that you sort of can switch the two partitions, or taking a prefix and then sticking it on the end as a suffix. Okay? So one thing you'll notice is that for this particular string, which was repetitive, right, bon, we actually arrived back at the original string before we'd done all 6 of our rotations. Okay, we have 6 rotations because there are 6 characters. So we can do this process 6 times before we're guaranteed to get back to the original string. This one happened to be repetitive, so we actually see a repetition here. I'll show it to you with colors. We see a repetition from between these two, between these two, between these two. Okay, so just making the point that when we take all the rotations of a string, we might get repeated rotations. Some of the rotations might be identical. I wouldn't have to change the string very much for that no longer to be the case, right? So if I just change the string to bonobo, for example, it should be easy to prove to yourself that all the 6 rotations of bonobo are going to be distinct because, for example, this n is distinct. There's no other n. So every time you go to rotate it, the n is going to be in a new position, and none of them could possibly be the same. Okay. All right. Rotation and notation. So next I need to talk about a bit of notation. Okay. So we all know dictionary order, right? When we go to look up a word in the dictionary, we're not confused about whether as comes first or ash comes first. And we're not confused about whether flower would come before flowers if we were putting a list of words in alphabetical order. we know the rule. The rule says that for cases where there's no actual character in the string to break the tie, that is to say when one string is a prefix of the other string, then the prefix comes first. So let's write an example. Let's just write our as and ash example again. So as we are comparing these two strings visually to see what's their relative order in the dictionary, we would compare the first character first. We'd see that they're tied, right, tie. Then we'd compare their second character next. So we'd see we see another tie. Then we'd get here and we'd realize we ran out of characters in the case of as. And we know that that means that as comes first, right? It's just a rule that we have. Okay? You might say, that's not just a rule, right? That's, universal law. But no, it's definitely not, right? Like we actually could have defined it the other way around. We could have just said that for any pair of strings, and if one is a prefix of the other, we could say the longer string comes first in the dictionary. We could have. I mean, that's not what we're used to, but we could definitely have defined the rule that way, and we'd still have a total order over all the strings in the dictionary. We just don't. It's a convention that we define it the other way. The prefix comes before the longer string. So, related to this sort of convention, let's actually solve it with notation so that there's no longer any question about what the convention is or should be, and we'll solve another problem at the same time. And we're going to do that by adding a special $ symbol. We're just making up a new symbol, right? $ is chosen because why would a word have a $ in it, right? So it's chosen so as not to be a typical character that you would find in a typical string. Let's say you did have strings that had $ in them. Well, then make it some other character, some other special character that does not appear anywhere else in any of the strings under consideration. It's a made-up character. So let's define a new simple $, which we call the terminator, and we just define it to be alphabetically first. It comes before A, it comes before punctuation, like it comes before everything. And we'd stick it on the end of every word, right? So if bonbon is a word that's in our data set, and let's say we're going to build some index data structure over bonbon, or we're going to take the Burrows-Wheeler Transform, as we'll soon see, of bonbon, then as a first step, we would stick this terminator symbol on the end. So the fact that it is not equal to any other character in the string, and together with the fact that it's alphabetically before all the other characters, means that $ does this, the tie-breaking work for us. We don't have to have a special rule about what happens when one word is a prefix of another. Okay? So, for example, let's say that we took the word bonbon and we took all of its suffixes. Okay? And obviously, without the $, we would have two suffixes, this one and this one, where this one on the bottom is a prefix of the one on the top, or this one in the middle is a prefix of the one on the top. Okay? If we don't have the $. But once we add the $, we have a situation that's much more convenient from the perspective of comparing these strings, which is that none of them can be a prefix of another. Right? None of them can possibly be a prefix of another. Right? The $'s in a different position each time. Even if without the $, one is a prefix of another, as we have here and here. When we go comparing the characters, we are guaranteed to break the tie as soon as we get to a $, in one or the other. Okay. So in some sense, it enforces dictionary order without us having to have a special rule, right? If there was as $ and ash $, and we knew that $ came before A, we would know where to find them in the dictionary. Similarly, thinking in terms of rotations instead of in terms of suffixes, right? These are suffixes. Let's think in terms of the rotations of the new string after we've added the $. This has the happy property that now no two rotations are the same. Right? Before we said, without the dollar sign, we actually would have had two equal rotations, bonbon and then the one corresponding to this row, but without the dollar sign, which is just bonbon again. But if we do this with the dollar sign appended at the beginning, then no two rotations can possibly be the same. All right, so this is a piece of notation. It's a definition that we're going to keep with us as we go along because it just generally simplifies. It simplifies the algorithms and it simplifies how we argue about those algorithms. Okay, so please don't be afraid of this dollar sign symbol. It's not there to confuse you. In fact, it's there to make your life simpler. Okay, let's define the Burrows-Wheeler transform, and I'm going to start with a sort of very operational definition, sort of by construction type definition of what is the Burrows-Wheeler transform. So let's go through it. So let's say we have an input string, and we've appended dollar sign, as we always will from now on when we're dealing with indexing strings. And we'll take all rotations of that string with the dollar sign. Okay, let's see. But first, we're going to sort them alphabetically. Okay, we'll sort them alphabetically. There will be a total order. There will be no ties between these rotations because, as we said, when we have the dollar sign, all the rotations will be distinct. Okay, so we're going to sort them. And that's going to give us a matrix, right? Because there are 7 characters in our original string T, including the dollar sign. So each row of this matrix is a rotation of a 7-character string. So there's going to be 7 columns for sure. And then there are 7 different rotations that we can make. There's 7 different ways of chopping the string into 2 pieces and switching the order of the 2 pieces, or 7 times we can take a character from the beginning and put it on the end. Right, so this is going to be a sort of square matrix, 7 by 7, but unusually it's not a matrix of numbers, it's a matrix of letters. And this is called the Burrows-Wheeler Matrix. We haven't yet said what the Burrows-Wheeler transform is, but it will often be convenient to think in terms of the Burrows-Wheeler matrix later when we make our arguments. So it's good to see the matrix. Okay, so there's the Burrows-Wheeler matrix. The Burrows-Wheeler transform is the last column of the matrix. So it's this. So the Burrows-Wheeler transform of this input string, ABA, ABA, dollar sign, is this string, ABBA, $AA. You might notice that this string is a permutation of the original string, right? The original string has, let's see, it's got 4 A's, 2 B's, and $1. And this has 4 A's, 2 B's, and $1. Okay? Now, is this true by construction, like according to how I just described, how we can obtain the Burrows-Wheeler transform? Yes, because let's look at the Burrows-Wheeler matrix here, and let's think about all of the rows and all of the columns and whether or not they are permutations of the original text. Let's start with the rows. The rows are easy, right? Each of the rows is a rotation, and a rotation is just a permutation. It's a kind of permutation. It's like a special case of a permutation. Okay, so clearly all the rows are permutations. Are all the columns permutations? Okay, well, one quick thing you can do is just look, okay? So you can look at the columns and see, do they seem to all have 4 A's and 2 B's and a dollar sign? And indeed they do. So that might be a good sanity check to do first. But then why is it the case that they're all permutations? It comes down to the fact that each row is a distinct rotation. Because each row is a distinct rotation, right? We don't have 2 copies of the same rotation in here. It's just all distinct rotations. Because it's all of them and because they're distinct, you can argue that each column of this matrix is also a permutation of the original string. Okay, so just like the first column, the last column is also a permutation of the original string. Okay? So that is the Burrows-Wheeler transform. But what's it got to do with coding? What's it got to do with compression? So that's what we'll see next. Okay, same example, same matrix. I just want to make, in order to make things a little easier to explain, I'd like to take sort of this last column and sort of chop it off. And instead of drawing it as the last column, I just want to move it over here and draw it as the first column instead. So let's do that. Okay, that's what I have here. So you can see what I have here is that last column, A, B, B, A, $A, A. So this is the Burrows-Wheeler transform of T. And then let's think about what's the relationship between what we have here versus what's in the Burrows-Wheeler transform. Okay, so for example, this A, obviously it was originally over here. But with respect to the original string, which A is this? Well, it's the last A. It's the A that comes just before the $sign, right? Remember, this is a rotation. This A is the A that came just before the $sign in the original string. It's that A. Okay? So what I have here is that A's right context. Okay, but when I say right context, now I mean that it's allowed to wrap around. It's like the right rotational context, right? So it's even though A is toward the end of the string, right? This is the end of the string, right? Right after $sign, the original string. We wrap around and we say that the rest of it is also context, right? So this is the right context for that A, which is that A, which is that A. Okay, this B is the last B in the original string, right? You can tell, right? Just look over here, right? You can see that this B is followed by $. So it's the last B in the original string. So it's this B. So this B has this as its right context, right? $, A, B, A, A. Again, it's rotational. So after the $, we wrap around and get the A, B, A, A. So this B is this B is this B. And this is its right context. Okay? This B is this B, and now this is the other B, so it's that B. So its right context is going to be A, B, A, $A. A, B, A, $A. Okay. You get the idea. For each character here in the Burrows-Wheeler transform, the row of the rest of the Burrows-Wheeler matrix, which I'm showing to the right now, is its right context. Rotational context with respect to the original string T. Okay. So what did the Burrows-Wheeler transform do? It took the characters of the string T with the $sign and it permuted them in such a way as to put them in order according to their right context. It put them in order according to their right context. Okay. So I'll hammer this home a little bit more, but that's the basic principle. So the Burrows-Wheeler transform is taking a string and putting it in a new order, but the new order is by context. Okay, so why might this be useful for compression, for encoding things, kind of like we were doing with our high-order entropy encoding schemes? Well, let's look at a larger example. It's actually very hard to see this with small examples, but it's much easier to see it with a larger example. This is a larger example from the original paper by Michael Burrows and David Wheeler. And in fact, the example that they're showing, I'll tell you what they're showing here. The example that they're showing is basically like the source code of their paper. So it's very self-referential. Now let me just be really clear about what's being shown here, because there's a blue rectangle and a red rectangle. The way you should think of what you're seeing is, let's say this here is the entire Burrows-Wheeler matrix. So it's a great big square. What is being shown here is just an excerpt. It's just a piece of that Burrows-Wheeler matrix. And in particular, it's the beginnings of a bunch of consecutive rows from the Burrows-Wheeler matrix in blue. So these are the beginnings of several rows of the Burrows-Wheeler matrix. Not surprisingly, you can see that they're sorted, right? Like, so this is alphabetically before this, which is alphabetically before this, etc. And you can see that they're all close to each other alphabetically. They all start with N space, and then either T or U or W. Okay, so this represents a chunk of the matrix that looks like that. And then what's lined up to its left, just like I did before, is the characters from the final column, from the Burrows-Wheeler transform, corresponding to those rows. So here they are. So these are this is a stretch of the Burrows-Wheeler transform here, and these are the right contexts of each of those characters in the Burrows-Wheeler transform. What you see here that's very interesting is that the characters in the Burrows-Wheeler transform are not random. They're very predictable. They are all vowels, and in fact, are there even any U's? No, there's no U's or Y's in here, so it's all A's, E's, I's, and O's. Why is that? Well, because conditioned on the context, and these are all very similar right contexts, conditioned on the right context, you tend to get a predictable character coming to the left, right? This is English text. You know, it's got an and on and in and stuff like that, and words that tend to end with ANs and ONs and INs. So it's not too surprising that we see a low diversity of characters here, right? It's kind of a much more predictable set of characters than we see if we look like in this column, like in one of the other columns. Okay? So again, it's just another example of because they are sorted by their right context, we are bringing together like characters. We're increasing the predictability. Okay, so this actually implies that we could use this for compression. And here's what the strategy would be if we used it for compression. The compression strategy would be, you give me a string, it might be a file off your computer. I'm going to tack on my imaginary $ character on the end, which is less than all other characters, and I'll get the BWT. We saw how to do that. It's not necessarily efficient what we saw, and there are much more efficient ways than what we saw, but we did see how to do it, right? We can form that matrix by sorting all the rotations and then take the last column. So we can get the Burrows-Wheeler transform of the text. We can then take that Burrows-Wheeler transform and partition it by K context. I'll show you more what I mean by partition by K context in a moment, but basically just imagine the Burrows-Wheeler matrix with horizontal lines through it, breaking it up into chunks of rows according to which rows have the same K context. I'll show you a picture. And then for each of those, we can take that chunk of the Burrows-Wheeler transform and encode it with a normal zero-order empirical entropy encoder like Huffman, for example. Okay? And if we can do that, right, compression is wonderful, but it's no good if you can't decompress it, right? So we have to be able to go backwards. So the decompression strategy is going to take these 3 steps and undo them in reverse order. So the first thing we have to undo is the H0 encoding, so we'll do the decoding. Right? We will have stored the codes so that we can do the decoding. We do that for each of the partitions, and then of course we must now concatenate the partitions to get back the full Burrows-Wheeler transformed string. But that's still not the original string, it's the Burrows-Wheeler transform string. So the last thing we have to do is we have to reverse the Burrows-Wheeler transform. Okay? Now we've got the original string back. And how much space did we need? We just really needed enough space to facilitate this first step, right? This step is, it's just concatenating. This step might need some space, which we'll come back to. But the main source of disk footprint or memory footprint is just going to be the codes required to do the decoding of each of the partitions. So it's really just mainly the H0 code for each partition. Okay? So we are using the Burrows-Wheeler transform to put the string in an order so that it is easy to get all the characters that have the same right context. And that allows us to therefore apply zero-order empirical entropy encoders within windows of the Burrows-Wheeler transform to achieve high-order empirical entropy style coding. Right? So we got high-order encoding, but from a low-order encoder, a zero-order encoder. The trick was putting the string in the correct order to begin with. So the Burrows-Wheeler transform is sometimes referred to as a compression booster. It itself is not compressing the string. It's just putting the string in a new order. But the new order is an order that sort of reveals the structure of the string so that a simple coder, a zero-order encoder, can be applied to it and it can get high-order coding style compression. Now, I haven't told you, by no means have I told you the whole story, right? For one thing, we have no idea how to reverse the Burrows-Wheeler transform to get back to the original string. That'll be the next video. In addition, some of these things, it's not clear whether they can really be done efficiently. But what I want to do to complete this video is show you in more detail what these 2 steps really entail. Okay, so let's consider a Burrows-Wheeler matrix. This is Burrows-Wheeler Matrix, obviously, for Mississippi. And let's say our goal is to build a high-order empirical entropy encoder, an H1 encoder, for Mississippi. How does the Burrows-Wheeler matrix, or how does the Burrows-Wheeler transform, help us to do that? Well, let's take this matrix and consider the first column, because if we consider the first column, these are basically all the first letters of the right context of the Burrows-Wheeler transform letters, right? This dollar sign comes to the right of this I. This I comes to the right of this P, rotationally. This I comes to the right of this S, etc. Right? So for these characters, their right contexts are here. So if I draw this line and I draw some other lines, what you're seeing is I'm dividing the Burrows-Wheeler transform by right context. Okay? So let me show this with cleaner lines. Right? So within this window, for example, these are the characters that have S as their right context. These are the characters that have P as their right context. These are the characters that have I as their right context. So if I wanted to end up with a high order coding scheme, I could apply a zero order empirical entropy encoder like Huffman within just these partitions of the Burrows-Wheeler transform. Okay? And I would get a resulting high order encoder, and I would get, by applying our formula, I would get that weighted average of the H sub 0 code lengths of the and then according to the definition of high order empirical entropy, what I'm getting at the end of the day is a H sub 1 encoding for T, which is nothing but this kind of weighted sum of the zero order encodings on the characters that have the same right context, right? It's exactly the same idea as before, it's just this time I achieved it by partitioning the Burrows-Wheeler matrix. And we don't have to stop at H sub 1, we could do a similar thing for H sub 2, where now we're taking 2 characters worth of context. It's not a wonderful example when my string is so small, right? These partitions have become very small, almost trivial, but you can do it up to any order, right? So we can obtain a high order code, an H sub k code, by applying a zero order encoder like Huffman in each k context chunk. Chunks of right context of 2, right context of 1, or the 2 that we just saw, but we can pick, right? Once we've got the Burrows-Wheeler matrix, we can pick any value we want as being the amount of context we want, and we can still use the structure, the order of the matrix, in order to quickly gather together the parts of the Burrows-Wheeler transform to which we need to apply the zero order encoder. We don't even need to use chunks that have identical right context. We could have chunked this a different way. We could have just put everything in, you should have just taken 4 rows at a time or something like that, right? I could have just drawn a different set of partitions. Let me just, for fun, let's say we took every 3. Okay. We could partition it that way and apply a zero order empirical entropy encoder in each of those partitions. And while now we are getting mixes of different right contexts within each of those partitions, you can imagine for a long string, there might be a very low diversity of right contexts. Even though they might be slightly different, they might all be similar. Like here, SI, SS, SS, these are different contexts, different right contexts, but they're similar. So it might actually be perfectly okay to not necessarily take exactly the groupings based on K context, but instead to just take somewhat looser groupings. The key being we put everything in the right order first, right? So we don't have to be exactly right about where we put these horizontal partition lines, but the order helps us. We could just take fixed length windows and the order helps us to be able to argue that they have similar right contexts.